Okay, so this is 6.1. For the next few sections, we're going to be talking about complex numbers. It might seem a little strange why we're doing this in a trig class, but we'll see in the next section, complex numbers and trig go very, very well together. There's very important kind of ties between the two subjects. Okay, so the first thing is a lot of people have seen complex numbers before or imaginary numbers and feel it's a really weird and unintuitive made up thing. But actually, in your math careers, this has been happening all through, your career in terms of learning math, right? So, for example, in first grade, what do you have to work with? You only have positive numbers, right? Everything is positive numbers, and the kind of math you do is 3 plus 5, 10 minus 6, and stuff like that, right? Okay, let me write first grade. Okay, at some point, maybe let's say third grade, I actually don't know how accurate these are, but sometime in the past first grade, you learn about fractions, right? So that's a completely new kind of mathematical object compared to what you were working with in first grade, right? In first grade, the numbers that you know basically are just 0, 1, 2, 3, 4, 5, 6, 7, and so on, right? But suddenly you have this new concept of numbers, or this new type of number, called a fraction, right? And it's, if you're a kid, right, it's not even a very intuitive thing, right? If in first grade, you might be talking about if you have two people and then in a room and then three more people come in, how many people are in the room? 5 people, right? But once you have fractions, what's half a person, right? What's a third of a person? What's 4/3 of a person? So, that's one example where, you have some idea of what math is, what numbers are, and then suddenly you're introduced to this new mathematical object, fractions. But, maybe it seems weird at first, but eventually you just get used to it and you work with fractions as if, just as comfortably as you work with, regular whole numbers, right? And then at some point in the future, maybe fourth grade, let's say, right, you're introduced to negative numbers, right? And that's again a very weird thing, right? Up to now, you're maybe only working with 0, 1, 2, 3, 4, 5 fractions, 1/2, 1/3, 4/3, and so on, right? So you're talking about 5 apples, half an apple, right? Which at this point makes sense to you now. But what's negative half an apple, right? What's negative 10 apples? So again, you had your previous conception of what math is, right? And then you're suddenly introduced to this new mathematical object, which perhaps seems weird, right? Again, what's negative 5 apples, right? But you get used to it, and then now, right, today, you work with negative numbers, you work with fractions, just as if they were whole numbers, right? You're as comfortable, hopefully, with these as you are with regular whole numbers, right? With just positive whole numbers. Okay, maybe a little bit later, sometime in high school, I suppose, right? Hopefully, you're introduced to the fact that not every number can be written as a fraction, right? So that there's some numbers which are not fractions, right? So the most famous example is pi, right? Pi cannot be written as a fraction, something over something. It's impossible. So these are the irrational numbers, right? And kind of in short, they're the numbers that have an infinite expansion when you write them as a decimal, right? Infinite non-repeating expansion. So pi is 3.1415, and it keeps on going infinitely, and it never repeats. And what happens is those guys cannot be written as fractions, all right? So here's another example where, you're comfortable working with all the previous kinds of mathematical objects, whole numbers, fractions, negative numbers, and suddenly you have this idea of an irrational number, which is very, very different, from all the previous numbers that you've worked with, right? Another example is root 2. That's an irrational number, right? 1.41 dot 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 dot. It keeps on going forever, all right? And exponential e as well. So again, this is very, very weird, but hopefully today, right, at this point, you work with, for example, pi, especially in our class, just as if it was any other number, right? We talk about pi over 4, pi over 3, very comfortably in our class, right? Everybody's very comfortable working with these numbers, hopefully. So again, you're introduced to this new concept, this new type of number, and after a bit, you're just very used to it. So complex numbers is the same idea. Once we introduce it, right, it seems a little weird, but once you kind of get used to it, it is just like any other number, right? So I think the feeling is a lot of students think that it's just this very, very special thing that's so different from what you've worked with in the past that it's just completely strange. But again, my point here is, right, this has been happening to you all through the years of your math career, right? And you've gotten used to all the previous steps of kind of new mathematics, and now complex numbers is just a next step in this process. All right. So what exactly are complex numbers? The idea is that we have, when you look at equations, right? So x squared minus 9 equals 0, right? So these guys can be solved. So this is x squared equals 9, which is x equals, we're square rooting both sides, so plus or minus root 3, right? Oh, sorry, plus or minus root 9, which is plus or minus 3. Okay, so a lot of these kinds of equations can be solved, but some of them can't be, right? So if you look at x squared plus 1 equals 0, and you try to solve this in the same way, this is x squared equals negative 1, and that would mean x is equal to plus or minus square root of negative 1, right? But that actually doesn't make sense. In fact, even the line above doesn't really make sense, at least up to now, up to today, because how can you square something and get a negative 1, right? When you square things, negatives always become positives, right? When you square minus 2, you get positive 4. So even here, immediately, you can see that there's no solutions, right, to this problem. And of course, in the next line, you can see that perhaps even more explicitly, there's obviously, again, up to today, there's no such thing as square root of negative 1, right? But in fact, what we can do mathematically is we can introduce a solution to this, right? So we're just going to say, I'm going to introduce a solution to this, and it's going to be called I, right? So make up, let me write it like this, make up new number, and I'm going to call it I, right? And that's the standard terminology. And the whole point of I is that I solves x squared plus 1 equals 0, right? So the point of I is that I squared plus 1 equals 0, okay? Or to write it, throw the one to the other side, I squared is equal to negative 1. Okay, so that's the whole point of introducing this new number or making up this new number, I. It's so that we can solve problems like this. And from here on out, we work with I as if it was just any other number that we've worked with in the past. Of course, to make a distinction between whether we're allowed to work with I or whether we're not allowed to, we talk about the situation where you don't have I, where I is not part of your kind of number system. We call those real numbers. And where you have I in your system, we call them complex numbers. All right. So again, it seems really weird, but again, think about maybe a problem like this, right? Maybe let's see. So we were talking about fractions, third grade, right? You're looking at fractions. So maybe before you learn fractions in second grade, if you're asked to solve 2x minus 1 equals 0, right? Or just, yeah, 2x minus 1 equals 0, that would be the same as 2x equals 1. But to a second grader who doesn't know fractions, there's no solutions, right? No solutions to second grader, right? And what do you do in third grade? You introduce the idea of a fraction. So third grade, you have the idea of x equals 1/2, right? And what's the point of x equals 1/2? In a way, you can think of it as it's a solution to this problem, right? And so now you have this new number that you work with. And again, by today, right, many, many years after third grade, you're very used to it. Okay, so I is exactly the same idea. It's the thing that we introduce where so that we have a number whose square is -1. All right. Okay, so again, the point of I is that I squared is equal to -1. And oftentimes, or sometimes, we'll write I equals square root of -1, like that. All right. But the preferred kind of notation, whenever you see square root -1, transform it into I. All right. Okay. By the way, we said I is the thing that it solves x squared plus 1 equals 0, right? I solves this. And again, it's the made-up number that solves it, right? Our new number in our mathematical arsenal. But notice that, of course, minus I also solves this, right? So as usual, there's two answers to this problem, right? Plus I and minus I. Okay, let's see. So at this point, when you do have expressions that have negatives in the square root, so for example, square root of -6, now this is in a way a legal quantity because you can think of this as square root of -1 times 6, right? And the square root, the property of square roots is that you can always break them up when they're products. So this is -1 minus 6, -1 positive 6 square roots, like that, right? And this square root -1, you think of that as I, or that is I, so minus square root 6i, okay? So square root of anything now is actually a legal quantity when we're talking about working with complex numbers. All right, so of course in the same way, square root of -2/3 is square root of 2/3 I. And now again, at least in these sections, these are perfectly legal numbers. Okay, so just as with in all those past situations where you kind of added new mathematical objects to your arsenal, all those new mathematical objects you could do kind of the same math as you could do previously, right? So before you had fractions, right, you could add whole numbers, right? After you have fractions, you can add fractions, right? Before you had negative numbers, you could, for example, add fractions. After you have negative numbers, you can add negative numbers as well. So every time you add a new kind of number to your mathematical arsenal, you always wonder, right? Can I do the regular arithmetic with this new concept, right? So can I add complex numbers, right? Can I add I to something? Can I multiply? Can I divide? And so on, right? And so that's what this section addresses. And the answer is, of course, yes. So we can, right, add. So for example, we can talk about 3 plus I, right? We can talk about I plus I, perfectly legal. We can talk about I plus 4, right? Perfectly legal. Okay. We can subtract. So I minus 3, 3 minus I, right? I minus I, all perfectly legal. Okay. Let's see. We can multiply, right? So of course, if we can add, if we have 3 plus I, that means we can multiply 3 plus I times whatever, right? Let's pick this one here, 3 minus I. That would be perfectly legal as well, right? So all the regular operations that we do with arithmetic, we can do with I, all right, with complex numbers. So today we're going to focus mostly on these four. Sorry, one more, powers. So you can do I to the 10th, right? Because normally, right, with regular numbers, 15, you can take 15 squared, 15 cubed, 15 to the fourth, whatever, right? So you wonder, can I do that with complex numbers? The answer is yes, right? I to the 10th. That just means I times I times I times I 10 times, right? So there's no problems with any of these concepts. So we're going to focus on mostly on these guys today, but you can do anything, right? So what else can you do with regular numbers? You can take powers in this way, right? You can take powers 2 to the I, right? Instead of I to the 10, you can take 2 to the I. That's perfectly legal as well, all right? We're not going to talk about that today, but it's perfectly legal. What else can you do with numbers? If you have a function, right, you can plug in complex numbers into the function, right? So whatever the function is, you can put in a complex number. So f of I, perfectly legal, all right? So if f of x is 2 to the x plus x, right? Then f of I would be 2 to the I plus I, okay? So everything in a way works just as before, except, we have this I floating about around, okay? All right, so it looks like now kind of working with these new numbers, with complex numbers, is kind of unpleasant. Because, right, this I, for example, when we look at this 3 plus I up here, this I doesn't really interact with the 3, right? So it looks like things look a lot more complicated. And in some ways they do, but in other ways they're not as complicated as it might appear. All right, so here's a fact. And we're gonna kind of confirm this fact for these 5 adding, subtraction, multiplication, division, and this version of powers. We'll confirm this today. All right. So the fact is that any complex number can be written as a plus bi, where a and b are real numbers. All right. So no matter what I did to my number, whatever operations I did, I can always write my answer as a plus bi. All right. So again, what I mean by a and b are real numbers is something like a plus 4i, right? 3 minus 10i, 1/3 plus 4/5 I, and so on. All right. So this guy, the 3 and the 4, the 3 and the minus 10, the 1/3 and the 4/5, those all have to be real numbers, right? Just the regular numbers you've been working with up to today. By the way, this 3 minus 10, technically, if you want to write it as a plus bi, it's actually 3 plus minus 10i. All right. But normally, this subtraction is, we're so comfortable with it anyway that writing it as 3 minus 10i is perfectly fine. Okay, so this is called standard form. This guy here, this form is called standard form. All right, so in other words, in short, any complex number can be written in standard form. All right, and we very much like to do this for a few reasons. One of them we'll see in the next section. Once you have a complex number in standard form, there's a nice way to draw it, to visualize it. All right. Number two, it's good to write numbers in standard form because just for communication purposes, right? Because if there's two ways to write a number, and I'm writing it one way and you're writing it a different way, then could be confusion between us, right? Where we think we actually are working with different numbers, but in fact they're the same, right? So that's why, for example, sorry. When you learn fractions, right, you're taught to reduce 4/6 to 2/3, right? So in a way, the 2/3 is kind of like a standard form because it can't be kind of simplified anymore. So now if we always kind of reduce our fractions, then my answers will, to a problem will be 2/3. Your answer might have been 4/3, 4/6, but when you write it into standard form, 2/3, we know that our answers are the same. So we can communicate kind of more accurately. All right. So that's another motivation for using this idea of standard form. Okay. So again, it's not even a new idea, right? This fraction idea, we're all very used to it. And this standard form idea for complex numbers is the same. All right. So what I mean by any complex number can be written in this standard form is all these numbers that I've written here, up here, well, a lot of them are already in standard form, but some of them aren't, right? So this 3 plus I times 3 minus I, the point here is that that can be written as something plus something I. All right. This 3 plus I over 4 plus I, that can be written as something plus something I, right? So that's actually really nice because this 3 plus I over 4 plus I looks very complicated. Whereas something in standard form looks very simple, right? Just a number plus another number I. Okay, so this is even true of I to the 10. This is true of 2 to the I, which again, we're not going to talk about today, and any other thing you do with a complex number, right? As long as whatever you've done to the I, or mixed it up, multiply, divide, put it into fractions, no matter what you do, it's always possible to put it into standard form. Okay. All right. So essentially, the rest of this section is figuring out how to write a complex number into standard form, right? Particularly the multiplication and division and power examples. All right. By the way, before we actually do that, let me write a couple bits of notation. So standard form is a plus bi. Again, a number plus another number I, a real number plus another real number I. Generally, we like to write the real numbers in front of the I, right? So 3 plus 4i as opposed to 3 plus I4. But that's just a convention thing, right? Oftentimes, you can treat I like a variable, right? Like the variable x. And it behaves in some situations very much like a variable x. All right, and generally we like to put x's behind our numbers. So we do the same convention here. There is an exception in the next section, but at least for this section, that's how we'll be writing all our complex numbers. All right, so that's a standard form. The new thing I want to talk about here is usually for real numbers, right? Up to now, we've been using x as our variable quite a bit, right? We also like to use y's as variables and so on, right? X's and y's, t's, numbers like those, or letters like those. For complex numbers, frequently when you have a complex number, you like to call it z, all right? Again, it's just convention so that when people see the letter z, they know, this is going to be a complex number. Okay, I highly recommend for mathematics classes, you cross your z because it's very easy to confuse a z and a 2, and you definitely don't want to make that mistake. Okay, so before we actually do any computations, while we have the z thing, let me introduce another bit of notation, z bar. All right, so this is called z bar. All right, and this is the, or at least that's how we say it, z bar. It's the complex conjugate. This is the official name for it, complex conjugate of z. All right, so what this is a minus bi. All right, so whatever sign you had in front of this b, you swap it. All right, so if z were 3 plus 4i, then z bar is 3 minus 4i. All right, if z were 4 minus 2i, then z bar would be 4 plus 2i. Okay, so you always just swap the sign, plus to minus right there, minus to plus. Only the sign of the I term. Okay, so notice this, this 3 right here, it stays as 3 on this side. This 4 right there, it stays as 4 on that side. Okay, so the complex conjugate is very important. We'll talk about it quite a bit in the next section. It has a nice picture when we draw the picture for z, and it has very nice interpretations. Or it has you'll see these guys show up naturally when we work with, for example, quadratic equations. All right. So again, that's just notation. Let's actually get into kind of the meat of the material. So again, our goal today, roughly, is to write complex numbers into standard form. So here's a complex number, 3 plus 4i. It's already in standard form. If I add 4 plus 10i, right, how do I write that into standard form? Well, this one is fairly straightforward. You have a 3-term, 4-term, they can go together, right? 4i, 10i, they can go together. And then you just, add the coefficients as usual, right? So 3 plus 4 is 7, right? And then 4i plus 10i is 14i, right? 4 plus 10. Okay, so this guy here, you're just adding the components. This is 7 plus 14i. All right. You're just adding component-wise, right? So here, this is the situation where, just think about if you had 3 plus 4x and you added that to 4 plus 10x, right? What would your answer be? It would be exactly the same idea, right? The terms with the x's go together. The terms without the x's go together, right? So 7 plus 14x, all right? So in this context, it's for this kind of a simple addition situation, just you can think of I just as like the variable x, okay? Okay, subtraction, same idea, 3 plus 4i minus 4 plus 10i. How would you do that? Well, this would be equal to 3 plus 4i, and that minus sign you can distribute into each of the two terms, so minus 4 minus 10i. And then so you would get 3 minus 4 is negative 1, 4 minus 10 is minus 6, so minus 1 minus 6i. All right, and again, very, very technically, this would be minus 1 plus negative 6i, right? In the most technical standard form, something plus something I. All right, but again, 99% of the time, this guy here is perfectly fine for us. Maybe less than 99, because we're gonna want the plus in the next section actually. So we're gonna actually want to write the plus like this here with the negative inside like this in the next section. But don't worry about that for now. Okay, so again, this is very similar to how you would have done 3 plus 4x minus 4 plus 10x. All right, so similar to. All right, so those are not actually so exciting. The real exciting ones are multiplication. So 3 plus 4i, and let's do 4 minus 5i. All right, so now we're multiplying. Okay, so we're starting out again with two numbers that are in standard form, or basically standard form. When we multiply them, we're going to get something that doesn't necessarily look like it's in standard form initially. But like we said, every number can be written in standard form. So our goal is to do exactly that. All right, so how do you multiply? Well, again, you multiply in the same way you would have multiplied this if the i's were x's. All right, so for the first step, at least. All right, so for the first step, just think of I as a variable. So when I multiply, this is a sum times a sum. So we need to multiply it out carefully, right? Let's see. So we get 3 times 4, which is 12. And then 3 times minus 5, which is minus 15i. 3 times minus 5i. 4i times 4, so that's going to be plus 16i. And then 4i times minus 5i. So the 4 times the 5 gives me minus 20, times the minus 5, yeah, gives me minus 20. And then we have the I times the I, so that's I squared. All right. So this is what you would have done if if I were just a regular variable like x, right? And then you would clean up a little bit. 12, 15, minus 15 plus 16 is just I, so 12 plus I. And then minus 20I squared. Okay, so this is not in standard form because we have this I squared, but we can use the fact that, well, you can use exactly the definition of I, right? That its square is -1, I squared is equal to -1, to simplify that term, right? So this is actually 12 plus I squared is -1, so minus 20 times -1, all right? So this is going to be 12 plus I, and then plus 20, so we ultimately end up with 32 plus I, all right? And so now this is in standard form, right? 32 plus a number times I. That number in this case just happens to be 1. All right. By the way, if you just have the number I, if you really want to be super technical about it, this is equal to 0 plus 1 times I. All right. So again, if you want to write it in standard form, A plus BI, right? Your A would be 0 and your B would be 1. Okay. Seems kind of silly to do this, but in the next section, we'll actually want to do this in many circumstances. And just a regular number, a real number, 3, you can write that as 3 plus 0 times I. All right. So A in this case would be 3, and B in this case would be 0. And that's perfectly legal. All right. So one thing you can see is that the regular numbers, the real numbers that you have been working with up to today, are a subset of the complex numbers. All right, so let's do another multiplication and then we'll talk about division. So if I have 3 minus 4I times 5 minus 3I, or let me use a different number, 7I, right? So that would be 3 times 5 is 15. 3 times minus 7I is minus 21I. Minus 4I times 5 is minus 20I. And then I've got minus times minus, so that's a plus. 4 times 7 is 28. And then I times I is I squared. All right. Okay, let's do a little bit of cleanup. This is 15 minus 41I. And then I squared, again, is -1. So this is 28 times -1, so minus 28. So altogether, we get minus 8 minus 41, minus 41I. Okay. So again, fairly straightforward. Of course, you want to be careful. You always want to multiply these out very carefully, right? All right. If you have a square, 3 minus 4I, it's the same idea, right? A square is nothing more fancy than 3 minus 4I times itself, right? So you could multiply that out and get, transform it into standard form. But if you're comfortable enough, you know that when you square something, when you square a sum or a difference, like in this situation, you're going to get the first thing squared, so 9. And then 2 times the two guys multiplied together. So 2 times 3 times 4 is going to be 24I. And then plus this last term squared. So 4 squared is 16, and then I squared. Okay. All right. Again, if you had just multiplied this guy out, you would get exactly the same thing. And then the I squared is -1. So 9 minus 24I minus 16, minus 16. And so this is equal to minus 7 minus 24I. Okay. Finally, here's a more abstract one, A plus BI. So this is a general complex number, right? And then A minus BI. Let's do that. So if I multiply this out, I'm going to get A times A is A squared. A times minus B is minus ABI. BI times A, which is plus ABI. And then BI times minus BI, which is minus B squared I squared. All right. So the interesting thing here is that this and this cancel. So you get A squared. I squared is -1, so you get minus b squared times minus 1. But we got two minuses there, so it's a squared plus b squared. Okay, so this is really interesting because what I've calculated here is if I call this number here a plus bi z, then this a minus bi is, we just said, this is z bar, right? It's the complex conjugate. So when you multiply a complex number with its complex conjugate, you always just get the a squared plus the b squared, right? In particular, that's just a regular real number. All right, so let me write real. All right, so this is actually super important. We'll see that next section. In terms of a numerical example, 3 plus 2i times 3 minus 2i is going to be 9 plus 4, which is 13. All right, and that 13 does have very interesting representation in the next section. Okay, what about division? So 3 plus 2i over 4, let's do plus 5i, right? So this guy here, how do we write this guy in standard form? So again, we've been promised any number can be written in standard form. So anytime you have a complex number, you would like to ask, how to write it in standard form. So the trick here is actually the same trick you used in algebra to translate something like this, right? 2 plus root 2, let's say 3 on top, to get rid of the root 2's in the denominator, right? So what you did there was you did 2 minus root 2, 2 minus root 2, you multiply that on the top and the bottom. And what happens is when you multiply the 2 plus root 2 and the 2 minus root 2 together, the roots will go away because the cross terms will cancel, all right? So here we do exactly the same thing. So we take, so why do we do that? The idea is that the issue with this expression here is it has an I in the denominator, right? So it's hard to play with. So we want to get rid of the I in the denominator. And that's the same as getting rid of the square root in a denominator, in algebra. So we're going to multiply this guy by 4 minus 5i, 4 minus 5i. All right. So notice, of course, this is the complex conjugate of the denominator here, right? 4 plus 5i versus 4 minus 5i. All right. And we're multiplying the same thing, of course, on the top and the bottom, right? Because we're not changing. If we do that, we're not changing our actual expression. Okay. So doing that, right, the denominator will always be nice and clean. It'll be 4 times 4, which is 16, and then plus 5 times 5, which is 25, right? And the reasoning for that is exactly the reasoning we did up here, right, with a plus bi, a minus bi. This time it's 4 plus 5i, 4 minus 5i. We're going to get 4 times 4, 5 times 5 plus, right? Again, technically you're supposed to FOIL it out, multiply it out, but what's going to happen is the cross terms will always cancel. Okay, so you can see this is great because the denominator now no longer has i's in it. It's just a regular number, all right, regular real number. The numerator, we're just going to have to multiply it out. It's going to look, perhaps not look so nice, but we don't care, right? It was the denominator that we cared about in this step. All right, so for the top, 3 times 4 is 12. 3 times minus 5i is minus 15i. 2i times 4 is plus 8i. And then 2i times minus 5i is minus 2 times 5 is 10. And then I squared. All right. Let's clean this up. This is 12 minus 7i minus 10. And then I squared is negative 1. Right? Again, that's the entire point of this, of making up this I business, right? Because that its square is negative 1. Okay, 16 plus 25 is 41, right? So the denominator is just 41. Okay, minus 10 times minus 1 is 11. So this is 12 minus 7i plus 11 over 41. So this is 23 minus 7i all over 41. And this is essentially in standard form, but if you really want to write it exactly in standard form, 23 over 41 minus 7 over 41i. Okay, and again, you see our conclusion is it's a number plus, well, minus in this case, a number times I, right? So that's standard form, okay? So even though our initial object looked very, very much like it wasn't, like something very complicated, it can actually be written again in standard form, all right? Okay, and you do this with any sort of denominators that have i's in them, right? So if I have 3 plus 2i over 2 minus I, then what I would do is I would multiply 2 plus I on the top and the bottom, and that would convert this guy into standard form, right? And again, the point of the 2 plus I is that when you multiply out the denominator, the I terms will disappear, the cross terms will disappear. Okay, what about 3 plus 2i over just I? Well, what you would multiply is minus I on the top, minus I on the bottom, if you want to follow the same pattern that we have been doing, right? Because I you can think of as 0 plus I. So its conjugate is going to be 0 minus I, right? Which is just negative I. Okay. Now you can see in this particular circumstance, the negatives are kind of redundant. But if you want to, again, this is if you want to always do it the same way, you could do it like this, all right? And in this case, of course, the denominator will be I times minus I, which will just be 1, all right? So this will be just 1 in a denominator, right? Because I squared is minus 1, and then you have another minus, so minus minus 1 is 1. And on the top, you'll get minus 3i minus 2i squared, but minus 2i squared is going to be plus 2, right? I'm going to stop writing over 1 because that's kind of silly. And so this is 2 minus 3i, all right? Okay, so a fun one for you to do, 1 over I, right, is what in standard form? Right? So this is actually, it seems kind of a silly and simple problem, but you can see this left-hand side is something very complicated, right? 1 over something is always complicated, right? 1/3 is in a way a lot more complicated than 3, right? But because you can write it in standard form, it's actually not that complicated. It's something that looks fairly simple. Okay, finally, let's talk about powers of I. So what about I cubed, right? How do you write that in standard form? Or I to the 4th, or I to the 219, right? Again, we've promised that any complex number can be written in standard form. So these three, you should be able to write them as something, a real number plus another real number times I. All right, so the way we do this is kind of nice. Let's just calculate a few of them, just brutal calculation. So first of all, I to the 0. Let me leave some space here. I to the 0. So anything to the 0 is 1. All right, so I to the 0 is also 1. I to the 1 is just I, right? Anything to the 1 is it's itself. I squared. Well, the whole point of I is that its square is -1, so that's -1. All right, what about I cubed? I cubed is I times, let me write it as I squared times I, right? From the property of powers, when you multiply something squared times something, right, you get something cubed, okay? Or the most brutal way to think of it is I squared times I is I times I times I, right? So you're multiplying I by itself 3 times, so that's I cubed, of course. All right, but the point of doing this is we know I squared just from the line above. I squared is -1, so this is minus I. Let's do the next one. I to the 4th. This is I cubed times I. But I cubed, we know from the line above. That's minus I, right? So I cubed is -I, and then times I, we're going to ultimately get minus I squared. I squared is -1. We have a negative in front, so we get +1. So that's just 1. All right? I to the 5th, that's I to the 4th times I, which is I to the 4th is 1 times I, so we just get I. Okay? Now, we're not going to do any more because what we should notice here is we have a pattern, every 4 of them are repeating, right? So I to the 0 is 1, and then it's I to the 1 is I, minus 1 minus I. And then we start over again at 1. Next one is I, right? So we're starting over kind of every 4 they repeat, right? So I to the 6 is going to be minus 1. I to the 7th is going to be minus I, right? So these 4, right, repeat the previous 4. Okay, and then if you do I to the 8, same idea. I to the 8 is equal to 1, and so on. All right, so they repeat every 4. All right, and in fact, if you did this one up here, 1 over I, right? 1 over I is I to the minus 1, right? That's the definition of a negative power. You'll have noticed that the repeating also works. I to the minus 1 also works going backwards in terms of negative numbers. So this is negative I, right? I to the minus 2 is going to be minus 1, and so on, right? So every 4, it still repeats every 4 if you go backwards, upwards, all right? All right, so again, let me just circle, right? I to the 0 is 1, and then I to the 4th is 1, and then I to the 8th is 1, right? So they repeat every 4, right? Let me just emphasize it one more time. I to the 1 is I, right? I to the 5 is I. And then the next one here, I to the 9th would be I. All right, let me actually write that down. I to the 9th is equal to I, right? So we have this repeating every 4. So this tells me that I can figure out, one thing before we continue, notice that the right-hand sides are all in standard notation, right? In standard form, right? So this allows me to write any power of I in standard form, right? So just by repeating every 4, I can figure it out, right? Now, obviously, if I'm asked I to the 21, I would rather not go I to the 10, I to the 11, and like that. I would like a shortcut, right, instead of having to list them all. And the way we do that is, let's actually do I to the 21. So I to the 21 is equal to what? Well, it repeats every 4, right? So what I'm going to do is I'm going to divide 21 by 4. That's 5, 20 here, and a remainder 1. Okay, so what does division do for me? What does it tell me? So what this calculation told me is that 21 is equal to 4 times 5 plus 1. All right? So this 4 right there is that 4 right there, right? This 5 right there is that 5 right there. And then this remainder 1 is that remainder right there. All right? So when you divide, one way you can think of it is you're breaking down your number, right, into pieces like this, right? Okay, why do I care about that in this context? Well, I to the 21 is equal to I to the 4 times 5 plus 1. That's our conclusion we got from dividing. We use our properties of powers that hopefully we're comfortable with. This is I to the 4 times 5 times I. All right, because when you have a sum in exponents, this plus that, then that turns out to be I to the this times I to the that, right? So let me emphasize that with I to the 1 right there. Okay. All right, now let's use another property of powers. When you have I to the 4 times 5, that's the same as I to the 4th to the 5. All right, times I. So that's another property of powers. If you stack powers on top of a number, on top of anything, that's the same as just multiplying the exponents to each other. All right, so I to the 4 to the 5 is the same as I to the 4 times 5. Why do we do that? Well, I to the 4th, we know, right? We just calculated that I to the 4th is equal to 1. And so this guy in the parentheses here, that's equal to 1 to the 5 times I, right? But the 5 is almost irrelevant because 1 to the anything is just 1. So this is just I. All right, so we end up with I to the 21 is equal to I. And again, I is in nice standard form. Okay, so this is really nice. This means you can do I to the anything, I to the 257, right? So you just divide 257 by 4, 6, 24, 17. Let me do something a little different from the example above. So let me do 59. All right. So this is going to be 19, and then 4, 16, and then the remainder is 3, right? And so what we get is I to the 259 is equal to I to the 4 times 64 plus 3, right? Our conclusion of division here is that 259 is equal to this business here. And again, if we want to write this very carefully, this is I to the 4th to the 64 times I cubed. But I to the 4th is just 1, so it's 1 to the 64th times I cubed, which is just I cubed, right? And I cubed, we know what that is. Let's scroll back up. I cubed is negative I, right? And so this guy here is negative I. So just by knowing I to the 0 is 1, I is equal to I squared is equal to minus 1, I cubed is equal to minus I, we can calculate I to the any whole number. All right. Okay, so that's all we'll do for this section. Like I said, you can have many other expressions involving I, and all of them you can transform into standard form. We're just not talking about a lot of them in this section, right? So 2 to the I, we'll talk about this later, all right? Or e to the I especially, or something like this. Okay, so in the next section, we'll actually relate all this stuff to trig.